Welcome back. I am Dr. Flux, and we are continuing with Module 5 about the biological foundations of psychology. Over the past couple of lectures, we've explored the nervous system and the brain's inner workings, how signals travel, how reflexes protect you, and how your body balances action and rest. But here's the question for today. How do we actually know what we know about the brain? Today we'll dive into the fascinating world of historical examples, lesion studies, real-life neurological cases, and the scientific techniques that help us piece together how the brain functions. And while our focus will be on these incredible stories and discoveries, I want you to keep this idea in the back of your mind. All models are wrong, but some are useful. It's been our theme for this entire class. The way we study the brain through case studies, split brain research, and modern imaging helps us to build models of how it works. Though these models aren't perfect, they do give us powerful tools to understand this incredibly complex organ. But let's start with some review. Which division of the nervous system prepares the body for relaxation? Is it A, the parasympathetic nervous system, B, the sympathetic nervous system, C, the somatic nervous system, or D, the central nervous system? The answer here is A, the parasympathetic nervous system, or our rest and digest system. Next up, which signal is integrated in the spinal cord before reaching the brain? Is it A, afferent signals, B, efferent signals, C, reflex signals, or D, sensory signals? The answer is C, a reflex. Reflexes are decided on in the spinal cord, circumventing the brain entirely to allow us to act rapidly to take care of ourselves. Today, we'll be looking at some famous cases and some groundbreaking research that opened windows into how the brain works. We'll explore stories of Phineas Gage, patient HM. We'll discuss how lesion studies in research animals help us dive deeper into this understanding. We'll explore Roger Sperry's revolutionary split brain research, which revealed how the left and right hemispheres of the brain handle different tasks. And we'll round it off by taking a look at modern brain imaging techniques before we conclude and review. As we explore these cases, remember that each one adds a piece to the puzzle of understanding the brain, but the full picture is still a work in progress. So how do we figure out what different parts of the brain actually do? One of the earliest and most powerful tools scientists have used is what happens when the brain is damaged naturally or when certain surgeries have unintended consequences. When someone experiences an injury or an illness that affects a certain part of the brain, it often leads to changes in behavior, personality, memory, or perception. By examining these cases, scientists can map out which brain regions are responsible for different functions. Let's start with one of the most famous cases in neuroscience, Phineas Gage. In 1848, Gage was working on a railroad when a freak accident caused a 3-foot-long metal rod to blast through his frontal lobe, and somehow he survived. But while his body healed, something else changed. Before the accident, Gage was a responsible, hardworking guy. Afterward, he became impulsive, rude, and unreliable. His friends said he was no longer Gage. This dramatic shift in personality gave scientists the first clues as to what the frontal lobe of the brain might be up to. It plays a big role in decision-making, impulse control, and social behavior. Another groundbreaking case is HM, short for Henry Molaison. HM suffered from severe epilepsy, and in an attempt to treat it, doctors removed parts of his hippocampus, a region deep in the brain. The good news was his seizures improved, but the bad news was that HM could no longer form new long-term memories. He could remember everything from before the surgery, but afterward, every day was like waking up for the first time. This was an induced case of anterograde amnesia, which we discussed in the unit on cognition. This case taught scientists that the hippocampus is crucial for forming new memories. Without it, you're stuck in the present, unable to store new experiences for the future. Now let's talk about a condition that's both fascinating and deeply disorienting: prosopagnosia, which is also known as face blindness. People with prosopagnosia can see faces clearly, but they can't recognize them, not even their own reflection. Imagine looking in the mirror and not realizing there's a person staring back at you. This condition is linked to damage in the fusiform face area, a small region in the temporal lobe specialized for recognizing faces. But it's more than just a quirky brain glitch. it profoundly affects people's ability to navigate social situations. Neurologist Oliver Sacks wrote about prosopagnosia in his famous book, The Man Who Mistook His Wife for a Hat. In it, he describes a patient who, quite literally, mistook his wife's head for a hat. It's a striking example of how specific and specialized the brain's functions can be, and how fragile those functions are when things go wrong. And while the story in this book is about one of his patients, Sacks himself also suffered from prosopagnosia. While historical cases of brain damage in humans, like Phineas Gage, provided critical insights into brain function, modern neuroscience takes a more controlled approach. Lesion studies in research animals. By deliberately creating targeted brain lesions, whether through surgical removal, chemical agents, or precise electrical techniques, researchers can observe the resulting behavioral and physiological changes to infer the function of specific brain regions. For example, lesioning the hippocampus in rodents disrupts spatial memory, highlighting its essential role in navigating and learning. Similarly, damage to the amygdala alters emotional responses, giving us a clearer picture of how this structure regulates fear and aggression. Take a look at these two videos. One shows a typical rodent response to something fear-inspiring. The second shows the rodent's response with an amygdala lesion. It acts pretty fearlessly. This was some of the initial research that helped us to understand that the amygdala plays a role in emotional processing. Now, because these studies allow for precise control over lesion location and extent, they provide a powerful way to link structure to function, a foundational goal of neuroscience. And with modern tools like optogenetics and reversible inactivation techniques, researchers can now study brain regions with even greater specificity, moving beyond permanent damage to temporary and reversible disruptions. But there's still ethical issues when trying to apply this in humans, so this research is reserved for animal studies. So far, we've looked at what happens when specific parts of the brain are damaged. But what if we disconnect the two sides of the brain entirely? That's a question Roger Sperry and his colleagues explored in their famous split brain studies. These experiments gave us some of the most fascinating insights into how the brain's left and right hemispheres specialize in different tasks, and how they work together to create a unified experience. The brain is split into two hemispheres, connected by a bridge of nerves called the corpus callosum. This bridge allows the two sides to communicate and share information. Each hemisphere controls the opposite side of the body. The left hemisphere is typically in charge of language and analytical approaches, while the right hemisphere is more about spatial awareness and object recognition. Even though the hemispheres have specialized roles, they usually work together seamlessly. But what happens when that connection is severed? To treat epilepsy, some patients underwent a procedure where doctors severed the corpus callosum. This stopped seizures from spreading between the two hemispheres, but it also created a unique opportunity to study how the brain's two sides function independently. At first glance, these split-brain patients seemed completely normal, but when scientists like Roger Sperry dug deeper, they discovered some fascinating quirks in how the hemispheres processed information. Here's how Sperry's experiments worked. Patients were shown images in one visual field at a time, meaning each image was only processed by one hemisphere of the brain. When an image was shown to the right visual field, processed by the left hemisphere, patients could easily name an object because the left hemisphere controls language. But when an image was shown to the left visual field, processed by the right hemisphere, patients couldn't name the object. Instead, they could draw it or identify it by touch, but they literally couldn't find the words to describe it. It was like the right side of the brain knew what was happening, but it couldn't tell the left side. And since the left side controls language, the patient was left speechless. One of the most famous split-brain experiments involved showing a patient two images at the same time in different visual fields. A chicken's claw was shown to the right visual field, processed by the left hemisphere, and a snowy landscape was shown to the left visual field, processed by the right hemisphere. When asked to pick related objects, the patient chose a chicken with the right hand, controlled by the left hemisphere, and a shovel with the left hand, controlled by the right hemisphere, because you need a shovel for snow. But here's where it gets interesting. When the patient was asked why they picked the shovel, they said, "Oh, that's to clean out the chicken coop." The left hemisphere, which controls language, didn't know about the snowy scene, but it came up with a logical explanation anyway. This is called confabulation, when the brain fills in gaps in knowledge with plausible stories. Let's do an attention check. Which hemisphere is typically responsible for language processing? A, the left hemisphere, B, the right hemisphere, C, both hemispheres equally, or D, the brainstem. If you said A, the left hemisphere, you've got it. The left hemisphere is usually where language lives, which is why split brain patients struggle to name objects seen and processed by the right hemisphere. So far, we've looked at how lesion studies and split brain research have given us powerful insights into the brain. But how do we actually see the brain in action without waiting for injuries or surgeries to give us clues? That's where modern brain imaging comes in. Technologies like fMRI, PET scans, and EEG allow scientists to observe brain activity in real time, opening new doors to understanding how the brain works while you're thinking, feeling, and even daydreaming. One of the most common tools in neuroscience today is fMRI, or functional magnetic resonance imaging. fMRI doesn't just take a picture of your brain, it actually shows where areas are active while you're doing different tasks. Here's how it works. When a part of your brain is active, it needs more oxygen. fMRI tracks changes in blood flow to those areas by looking at blood oxygenation. This creates a detailed map of brain activity. This has helped scientists identify which regions are involved in things like memory, emotion, and decision-making. Another powerful tool is the PET scan. PET stands for positron emission tomography. PET scans track how much energy different parts of your brain are using, looking at metabolism. Scientists inject a small amount of radioactive material into the body, which highlights areas of high metabolic activity. This helps researchers study everything from normal brain function to disorders like Alzheimer's disease, where changes in metabolism can reveal disease progression. While fMRI and PET scans focus on blood flow and metabolism, EEG takes a look at something different: your brain's electrical activity. Here's a picture from me many years ago in 2013, working with my colleague Katya during Brain Awareness Week at the American Museum of Natural History in New York City. EEG stands for electroencephalography. It uses sensors placed on the scalp to detect electrical activity happening beneath it in the brain. We often talk about this electric activity as brain waves. These waves change depending on whether you're sleeping, relaxed, or alert. EEG is especially useful for studying conditions like epilepsy and sleep disorders, and it gives us a real-time view of how the brain responds to stimuli. Here's how I like to think about these tools. Imagine looking at a city from above at night. fMRI shows where the lights are brightest. It tells you which areas are the most active. PET scans reveal which neighborhoods are using the most energy, giving you a sense of the city's metabolism. EEG lets you hear the hum of electricity running throughout the entire city, capturing the rhythm of its activity. Each tool gives us a different perspective on the brain, but none of them tell the whole story. They're pieces of the puzzle, helping us build more complete models of how the brain works. Take a second to reflect on that. Each of these tools, fMRI, PET scans, and EEG, give us valuable insights into how the brain functions, but they also have limitations. fMRI shows us where the activity is, but it doesn't tell us why it's happening. PET scans highlight energy use, but they can't capture the complexity of how different brain regions interact as well. EEG measures electrical activity, but it lacks the spatial resolution to show exactly where the brain activity is happening. The brain is far more complex than any single scan can ever reveal. All right, we've covered a lot today. We've explored how natural brain damage or medical cases like those of Phineas Gage and HM have showed us the role of different brain regions. We've seen how scientists use lesion studies in animal research. We've seen how split brain research uncovered the specialized functions of the left and right hemispheres. And we've looked at how modern imaging tools like fMRI, PET scans, and EEG allow us to watch the brain in action. But here's the thing. Even with all this knowledge, the brain is still one of the most complex, mysterious systems we've ever studied. That's why I want to return to the quote I always discuss. All models are wrong, but some are useful, by George Box. In science, especially in psychology and neuroscience, we use models to simplify complex systems so we can understand them better. The story of Phineas Gage helps us to model the role of the frontal lobe in personality and decision-making. HM's case helps us to model the hippocampus and understand its role in memory formation. Split brain studies model how the left and right hemispheres specialize in different functions. And fMRI and PET scans help us model brain activity in real time. But none of these models tell the whole story. The brain is more complex, more dynamic, and more interconnected than any one study or scan can capture. That's why all models are technically wrong. They're simplifications, but they're also incredibly useful because they give us the tools to keep exploring and refining our understanding. Why does this matter? Well, understanding how the brain works helps us to understand ourselves and the people around us. Knowing how the frontal lobe affects decision-making can help us understand why someone might act impulsively after an injury. Understanding the role of the hippocampus helps us to grasp what it means to lose memory and how that impacts identity. Learning about split brain patients helps us to understand the impact and the influence of the different hemispheres. And using all of these tools helps us to build more effective models. Each model brings us closer to understanding the beautiful complexity of how we think, feel, and experience the world. Science is always evolving, and our models will constantly change as we make new discoveries, but each step forward helps us to see things a little more clearly. Before we wrap up, let's do a bit of review. Which technique allows researchers to observe brain activity by measuring blood oxygen content? Is it A, EEG, B, fMRI, C, lesion studies, or D, a CT scan? The answer here is fMRI, which takes a look at how the brain uses oxygen to understand where activity is taking place. Which patient can help scientists understand the role of the frontal lobe in personality and decision-making? Is it A, Phineas Gage, B, patient HM, C, split brain patients, or D, Broca's aphasia? If you answered A, you're correct. Phineas Gage's railway accident gave us much greater insights into the role of the prefrontal cortex in decision-making and personality. I encourage you to keep thinking about how these studies and tools shape our understanding of the brain and how they fit into the bigger picture of psychology. The brain itself is always in flux. It's constantly changing, adapting, and evolving, and so is our understanding of it. Our models help us make sense of this complexity, but there's always more to discover. That's the beauty of science. It's a journey, not a destination. And as we keep learning, we get closer to understanding not just how the brain works, but what it means to be human. Thanks for joining me today. Until next time, stay curious, stay resilient, and above all, live life in flux. I'll see you real soon. Flux out.